Hello student, in this video we're going to go over the first part of chapter 10, ANOVA, Analysis of Variance. There's two approaches covered in this chapter. One is an F-test to determine if two variances are equal. It can be a one-tailed or two-tailed process. And then the second part of this chapter looks at it also at an F-test to determine if three or more population means are equal. So in this first process, looking at an F-test to determine if two variances are equal, just as a reminder that in previous chapters, chapter 8, we developed an hypothesis test for the mean, as well as for the proportion. So this first process is just looking at an hypothesis test for the variance. It can be, as I said, one-tailed or two-tailed. So comparing two population variances, we have either two population variances or we have two other situations. We have the variance symbol from one equals the variance from that second population, alternately that they are not equal. It could also be written as a one-tailed test, such that variance from one is greater than and equal to variance of two, alternately variance of one is less than the variance of two. It uses an F-test. So the test statistic is variance from 1 divided by the variance of 2. Just as a note that, let's take that out, that the variance denoted as population 1 is the one that's greater. So we always have the larger variance as the numerator and the smaller variance as the denominator. So that's how we use our test statistic. The critical value, divide alpha by 2 if it's two-tailed. Degrees of freedom, n-1 in the numerator and n-1 in the denominator. The populations may have a different sample size, so that's why we have two different types of degrees of freedom for this test. So let's look at this example. This is an example I went over in class, but it wasn't written as clearly as it should have been. But here's a better rendition of it. So a packing plant packs cartons with jars using two different machines. It's believed that the average rate for both machines are the same, but there might be a difference in the variance of the two machines. The variance measures, once again, how spread out the values are. So even though on average they're the same, one machine could have a bigger variance, and then you're not going to get precise measurements. So there are 7 new machines and 8 old machines. Using 10% level of significance, is there a difference in the variation in packing time using the two machines? So this is a two-tailed test. It gives us some data, the standard deviation for the new machine and for the old machine. So I'm going to go into an Excel file here. Copy down some of this data we have. We're testing at 0.1 level, 10% level of alpha. The standard deviation for the new machine, 9.6609. Old machine, 4.1382. Sample size, 7 new machines, 8 old machines. So the test statistic uses variance in its equation. So one thing we have to do here is we have to calculate the variance from the standard deviation. The variance from the standard deviation is just the standard deviation squared. So those are the two values for the variance. The new machine is going to be viewed as population 1 because it's larger. This value, 93.33, is larger than 17.12. Therefore, the new machine, population 1, old machine, population 2. The test statistic is basically taking the larger variance divided by the smaller variance. So in this case, we're going to have, I'll just write this out here, 93.33, 17.12. So that equals, that is our test statistic, 5.45. One thing we want to find is our critical value. It has, remember, it has n-1 degrees of freedom in the numerator and n-1 1 degrees of freedom in the denominator. These are the sample sizes, so those are the respective n values for the two different populations we have. So we're going to have 6 degrees of freedom. Well, first of all, alpha is 10%, but this is a two-tailed test. Let's write down, we know it's a two-tailed test because in the question, basically, it's asking for this: is there a difference? And that denotes that they're looking for either a positive difference or a negative difference, an overall difference. So we could write the null hypothesis basically being, you know, I'm not going to use the symbols. Variance from 1 is equal to the variance from population 2. Alternately, the variance from population 1 does not equal the variance from population 2. And if my writing board were working, I could write this on in more using, you know, more proper statistical symbols and stuff. But this is good, except for my silly spelling mistakes right there. Okay, so we know it's a two-tailed test. So the critical value for alpha is going to be based on using alpha divided by 2, which equals 0.05. Degrees of freedom in the numerator is 7 minus 1. And degrees of freedom in the denominator, it's going to be 8 minus 1. So there we have, we go to our F distribution chart. We're going to be looking at 0.0, we'll be using a 0.05 chart. Let's get rid of these yellows here. And we have 6 and 7 degrees of freedom. 6 degrees of freedom in the numerator and 7 degrees of freedom in the denominator. So our critical value is 3.87. So let's just write that there, 3.87. Your decision rule is to reject the null hypotheses, as always, if the test statistic is greater than our critical value. So we're looking at these two values here. We are going to reject the null hypotheses because the test statistic is greater than a critical value, which means that we are left with this one, that the variance from population 1 does not equal the variance from population 2.